Okay, I have 2 past the hour, so I will start. Thank you, everyone, for attending the last of the 2023 Athena seminars. We will not be having any webinar in December because it's December and everybody is quite busy, but we will be restarting in 2024 with new topics and working on the new Athena mission, which, as I hope everyone has heard, has now gone through all of the proceedings and is on its way towards approval. Obviously, there are still many steps left, but we're looking much, much better than we were, say, earlier in the year. So thanks to everybody who was involved in New Athena for making that happen. This was not an automatic or an obvious process, but it seems to have been extremely successful. So with that, I would like to introduce today's speaker. We have Professor Monica Colpi from the Department of Physics at the University of Milano Bicocca, which is where I was going to start. That was the one I knew I was going to mess up. She got her PhD from the University of Milan in 1987 and then visited Cornell, and it was a postdoc at the International School for Advanced Studies in Trieste. She has broad research interests covering everything from theoretical astrophysics and relativity theory, black holes and accreting sources, neutron stars, transients, millisecond pulsars, and also now, as you'll see, interactions with gravitational waves as well. So she is actively developing on core science for the LISA mission, and we'll be talking today about the synergy between Athena and LISA in looking at massive black hole binaries. Very welcome to have you here, Professor Colpi, and please begin.
Well, good afternoon, and really thanks for the kind invitation. It's a pleasure to give this Athena webinar. Just giving an overview of what is, in my view, the next challenge we have ahead in the next 15 years, when LISA will, for the first time, detect the gravitational waves that are emitted during the merger of black holes as masses as, say, million solar masses, like our Milky Way black hole. So let me start taking you to a journey to a relatively nearby galaxy where 2 black holes that are spinning are embedded in a hot and tenuous plasma, magnetized, and so they start accreting, developing shocks, and so we hope that they are going to emitting X-ray flashes. You here see from a GRMHD simulation the last few orbits. So the 2 black hole comes closer, the new black hole that has formed is being recoiled because gravitational waves are carrying away linear momentum and is dragging with it a gas. So the natural question is, shall we see some electromagnetic emission companion to the X-ray, to the gravitational wave signal? So let me tell that indeed massive black holes that merge in the aftermath of major mergers are really our new multi-messenger source. So LISA will detect the chirp signal, the inspiral, then the merger, and the ring down of the black hole. And during the early inspiral phase, especially for the loud sources, we will be able to infer from the waveform the chirp mass, which you can see it's a combination of the masses of the 2 black holes and also the inclination of the binary relative to the line of sight. During the very late inspiral, at the time of merger, and in the ring down phase, when the black hole is ringing and oscillating, then we can determine the masses and the spins with a very high accuracy. I will be precise later on. And unique of merging black holes is that the signal, and unique of gravitational waves, is that the signal contains the measure of the luminosity distance. And if we are able to localize the source, then we can alert electromagnetic telescopes, radio or optical or X-rays, and hope to detect a light curve or a spectrum that could really tell us also what is going on to the gas, which is in the surroundings of this major and violent event where really space-time is changing dramatically. It is clear that the science return of coincident gravitational waves and electromagnetic observations using these sources that we call bright standard sirens is, in my view, really immense. In the domain of physics and cosmology, we will set even more stringent limits on the speed of gravitational waves, the perturbation of space-time, traveling at the speed of light according to general relativity, and also their propagation properties, whether they carry more than two independent polarization states, if there is a violation compared to general relativity. But since we measure the luminosity distance, in case we are able to identify the host galaxy and measure the redshift, then we can infer the luminosity distance versus redshift relation without using standard candles. This is why we call these binaries bright standard sirens. And so do cosmography, and hopefully to determine at least the Hubble constant or even the equation of state of dark energy, with a precision that could really be important to solve the tension we have in the measurement of H0. But from the point of view of astrophysics, which is the one I will focus on my talk, is that if we detect precursor emission in the spiral phase, we can really learn about accretion flows in violently changing space-time. And at and after the merger, we can learn about the merging of this new horizon and also learn about how fast the black hole is recoiling, because the recoil velocity is also associated to the spin magnitude, the mass ratio, and also how the spins are oriented. Let me just say few words about LISA that is about to be adopted in early January. I want you to imagine LISA as a way, or let me say that in order to measure gravitational waves, we need to have as probe freely falling test masses. So LISA is just a triangle. At the corners of this triangle, there is a spacecraft which is housing two freely falling test masses. And so the triangle has a size of 2.5 million kilometers. So LISA can really detect the space-time perturbation on a size which is comparable to a fraction of an astronomical unit. So it is sensitive to gravitational waves in between 0.1 millihertz to 1 hertz. And this is the best window to really detect the signal from merging black hole. LISA is an all-sky monitor, And during its motion of the constellation and around Earth, it can localize the source. And so this is very important in order to find an electromagnetic counterpart. The key sources, among the key sources of LISA will detect more than 10 to the 4 continuous signals from galactic binaries. But what we expect LISA to be revolutionary is in detecting the gravitational wave signal from merging massive black holes. In this figure, we see the characteristic strain, so the amplitude of the gravitational wave versus frequency. Here I'm showing the LISA sensitivity curve, and all sources that above this curve can be detected with a very high SNR. So here I'm depicting the Fourier evolution of 4 massive black hole binaries with different total masses. You can clearly see that it is particularly loud, the signal coming from binaries having a total mass of a few times 10 to the 5 solar masses. So we are talking about black holes that are not the one we see in the electromagnetic sky. As we move to lower masses, the signal is very long because we see very many cycles before the horizons of the black holes are touching. And as we move instead to higher masses, the one that maybe can be associated to an electromagnetic signal, the signal is shorter lived, and it has a somewhat weaker signal to noise ratio. But in this, these are sources that are placed at redshift 3 and have a mass ratio of 2. LISA can see almost the entire universe. I'm showing in this view graph what we call the waterfall plot. These are lines of constant signal to noise ratio in the plane redshift, cosmological redshift, versus the total mass of the binary. And so we can really detect with a signal to noise ratio larger than 10, merging binaries that are even beyond the redshift of cosmic reionization, so we can really pierce deep down into the cosmic dawn. And the best window for detecting the signal is in the relatively narrow band between 10 to the 5 and 10 to the 7 solar masses. But as we move to lower and lower redshifts, the SNR at merger, so integrating over the entire in spiral merger and bring down, can really be huge. And so we can have a very precise information on the parameter of the sources. So we can, on one side, learn about the black hole growth and assembly in our universe, so we can learn about the origin of massive black holes, which is still unknown, whether they come from massive stars or whether they come from heavy seeds resulting from the collapse of very massive stars. And here I'm just showing that during their evolution, there is time for them to accrete. So accretion is a process which is accompanying their pairing inside merging galaxies before we witness at the actual merger. But let me mainly focus, call your attention to low redshift mergers for which we have an SNR, which is extraordinarily large, more than 10 to the 3, 10 to the 4, which means that we have a lot of information carried in the waveform to extract beautifully the parameters of the source. And in this table, I'm just reporting our ability to measure the masses of the individual black holes to a very high precision, the total mass in the source frame, the luminosity distance, which can give also an information on the redshift. Here, each number is the median estimated over a population of mergers with a mass ratio between 0.1 and 1. So we are exploring a relatively wide range of mass ratios because we really don't know how efficient is the pairing process that lead the two galaxies to drive the black hole down to the scale where gravitational wave can dominate the dynamics. But for relatively nearby sources, we can measure with extraordinary precision also the spin of the primary and the inclination. So in general, near cosmic reionization around redshift 7, the uncertainties in the source frame total mass range from less than 0.001%, and in the worst case is 30% for the heaviest binaries, because the heaviest binaries have a short-lived signal in the LISA band, but when we move at redshift 2, near the peak of the cosmic star formation rate, the SNR are so large that we can have an exquisite determination of the parameters. We might have already today first evidence of a population of supermassive black hole binaries that has been detected through the low frequency, the nanohertz band from the pulsar timing array experiments. But let me, that are indicating, so that there is a strong and compelling evidence when it will be confirmed that we have a population of binary black holes that are certainly fated to merge within 10 to the 3 or 10 to the 4 years. So we have evidence that nature is really driving black holes that at the beginning are separated at kiloparsec scale and that they merge at microparsec scale through processes, dynamical processes that I don't have to really describe. But it is a very, very good news for us. But also I'm noticing that the mass range that the pulsar timing array is probing is in a sense complementary to the mass range that LISA will probe. And so we have also to face with the fact that when we consider the population of active galactic nuclei, which is depicted in this plane, redshift versus masses of the individual active galactic nuclei, and these little red dots are the very high redshift universe that are in place near the epoch of cosmic reionization. Electromagnetic observation clearly favors at high redshift the most massive quasars and active galactic nuclei, and we have to move down to lower redshift in case we want to detect the Milky Way-like black holes that are the one that LISA is sensitive. So it's interesting to notice that whereas LISA will detect at low redshift the most powerful sources of gravitational waves, electromagnetic observations in reality have refer to detections of relatively dim AGN. And so we have to find a compromise. If you want to detect an electromagnetic counterpart, the best region in redshift and mass space is exploring relatively low redshift mergers and with relatively light and dim active galactic nuclei. It was 2019, and Gunther Hasinger asked us to explore what can LISA do together with Athena, and we came up with this cartoon that I think it is really capturing the essence of what we would like to realize if, hopefully, Athena will join LISA, considering that LISA, if it will be launched in 2035-36, will take 2 years to reach the configuration for the constellation to rotate around the sun, while Athena will reach in its place faster. And so we might really have contemporary observations of a joint electromagnetic and gravitational wave signal. So the picture we were considering and studying is the following. So LISA can detect these relatively high GW high signal sources in gravitational waves 1 month before the merger. And we can have information on the date and time at which the 2 horizons of the black hole will touch. But we don't have any information on the position in the sky. LISA is a multi-sky monitor, and so it is very difficult to assign a region in space to locate the source. But as the in-spiral phase progresses, LISA can really collect more data and improve the sky localization that I'm showing in a moment. When the uncertainty region is around 10 square degrees, the uncertainty of the LSST, the telescope, we might consider that Athena can start scanning this region to look at the source within this wide field of LSST for reference, so in the optical. And this can occur, let's say, a week before the nominal merger. But as we approach the merger, say 10 hours before merging, the sky position gets smaller and smaller and smaller. And so it can be within the 0.4 square degrees of the Athena field of view. And then from this moment on, if the X-ray emission is sufficiently loud, can really join the extremely loud signal coming from this relatively nearby merger. And so we can witness the onset of a relativistic jet and X-ray emission from gas, which is swirling around. So we started thinking how these 2 universes come into intersection, really, which are the masses and the redshift range that can be consistent with contemporary observations of both gravitational waves and X-ray light. So we then ask whether the LISA sky error is sufficiently small to really match the field of view, let's say, of Athena, because this is what matters today. Can we really make it? At which redshifts, and which is the X-ray luminosity that we are expected? Indeed, if the system sourcing the gravitational wave signal is this system electromagnetic enough bright to be above the detection limit of any electromagnetic observatory. We might have also radio emission joining the X-ray one. And what is really important is whether the electromagnetic source is going to display a smoking gun signature either in the spectrum or in the light curve that would tell us unambiguously that what we see is just the counterpart of the gravitational wave source. If this is occur, we call it a true bright standard siren. Also, it is very important to know how many galaxies and active galactic nuclei are in the LISA field of view, because we might really misidentify the galaxy. And so we are misidentifying the redshift that comes from the light of the galaxy to perform the test on the luminosity distance versus redshift relation to which is relevant indeed from cosmology. And so let me enter into the realm of electromagnetic observations. Where do we stand now, and where we hope to stand when LISA will detect the gravitational waves? We have confirmed dual AGN in the optical and in the X-rays. So we know that there are galaxies housing black holes that are active during the merger, but these two black holes are still really far apart, and they are dragged to the scale of the milliparsec, where gravitational waves are taking over. Well, after a really long journey with the shrinking of the binary by the interaction of stars and gas. But we have one case that was discovered relatively recently of a very nearby, which is a very good news, of two dual AGN at projected separation of only 230 parsecs. We have claim of active galactic nuclei displaying periodic light curves in the optical, but we know that the baseline is so is too long, and so we might not see a fraction of a periodic light curve that could track the orbital motion of the two black holes that are accreting individually from two independent accretion disks. We might have velocity shifts in the emission lines that could be attributed to a shift in the broad line region relative to the narrow line region, but the candidates are still uncertain. And in general, they require observations of massive black hole, the one that Lisa is not really seeing. So as of today, we don't have any evidence of AGN transient emission that could be associated to a coalescence event consumed over a time scale, as we said, weeks, for the weeks, days, and hours when the merger is ongoing. And also we know little about the accreting black holes of 10 to the 5 and 10 to the 7 solar masses, their bolometric correction, the spectral and time variability, and the level of oscillation. So we have to really rely on theoretical modeling and on simulation and on simulating observational strategies. So the question we would like to know is whether in the pre-merger phase we could see a counterpart during the first weeks, and how strong it is, and whether we can also see the merger. So let me just take you into a simulation by Franchini et al. It is a Newtonian 3D simulation. Here you have two black holes that are embedded in what we call a circumbinary disk. This could be really present in the last 100 years, in the last month or so of a merger. And what has been discovered from both GRMHD simulations and even in Newtonian simulation, that the black hole quadrupolar gravitational field is is trying to excavate a cavity around the circumbinary disk. But thanks to the viscosity, viscosity is trying to bring the gas back toward the two black holes. So there is a counterbalance between a quadrupolar moment that is expelling the gas and the viscosity that is instead promoting the inward drifting of the plasma. And the key discovery of the last, let's say, almost 5-10 years is just depicted in this figure from Bowen et al. This is a GRMHD simulation, which is showing clearly that the two black holes, this big black dot is just an excision region. So imagine that the two black holes are now emitting gravitational wave because they are driven at a distance of sub-milliparsec scale, and they are surrounded by circumbinary disks. But the beauty of this finding is that the feeding of the black hole occurs through two mini disks. So the cavity that was expected to be empty of a plasma, it has been instead found to be filled by a lump of material, which is periodically feeding the two black holes. So the two black holes are really surrounded by two accretion disks. And this would be the clear theoretical motivation to expect to see an emerging X-ray emission that could be associated to periodicities that are commensurate to the fluid pattern. So the beat frequency between the orbital frequency and the orbital frequency of the lamp, which is the orbital frequency at twice the orbital separation, Keplerian frequency, or even periodicities that are really associated to the orbital motion. So these two mini disks that we call are feeding the black hole, and if the black hole are spinning, then it's clear that we can also enhance their the emission if they are spinning with a spin that are oriented parallel to the orbital angular momentum of the disk. There has been calculation on the expected spectra, and we see that the X-ray spectra, so we have a broadband emission from the optical to the X-rays, or even up to the very hard X-rays, coming from different contributions. So the mini disks are mostly responsible for the X-ray emission, whereas the cavity and the circumbinary disk is responsible for the optical emission. And it seems that the radiative efficiency is not very diverse to what is less than the one from the Novikov-Thor model, but still we really have indeed emission. But there is a worry that as we approach the merger, when the gravitational wave signal is capable to pinpointing the position in the sky, here is a simulation. The two mini disk, sort of the Hill sphere, the Roche lobe over, so the Hill sphere which is surrounding, this is the Hill sphere which is surrounding the two black holes, is being depleted because it is shrinking. And so it is really possible that we see a dimming of the expected emission from the disk, the emission that we expect coming in the X-ray. So maybe the signature which is accompanying the gravitational wave signal is not a brightening of the source, but it is a dimming of the source, but with some periodicity which is commensurate to the frequency of the orbital motion of the two black holes. When the black hole has merged, it can hit the cavity that has been created due to the balance between the accretion and quadrupolar torque, and can outshine in the post-merger phase. So we might see the precursor, and we might see the afterglow emission, the post-merger, but depending on the direction of the spin relative to the plane of the circumbinary disk, if the kick is perpendicular to the disk is really dragging most of the material which is bound. And so it can really outshine relatively early after the merger. So we cannot wait a year, but say days or weeks after the merger, so we can make a temporal association. Or it can really just pierce down into the disk when the spin are parallel to the orbital angular momentum. So depending on the spin alignment, we might have completely different afterglow emission, and we also might expect the launch of a jet, as it has been studied recently by this paper. In this paper, with time delays which come from days to months, and we would like not to have months, we would like to have days, because since we have the time of the merger and we have a relatively good localization, we can really point an X-ray telescope. But how well can we localize the source? This is something we could do with our current knowledge of the waveform coming from both numerics, especially from numerical relativity. So the message that so we studied relatively recently 3 binaries. Let me call a light binary with total mass of 3 × 10⁵ solar masses, and intermediate binaries like 2 black holes, Milky Way-like black hole, and a heavy binary of 10⁷ solar masses. more massive black holes have so short-lived gravitational wave signals that are just a burst, and they become weak because the sensitivity of LISA is decaying dramatically above 10 to the a few times 10 to the 7 solar masses. And here, so we studied binaries with mass ratio between 0.1 and 1 because we don't know the mass ratio between the two binaries. And the message here is that if you place this binary at a relatively nearby redshift, the signal to noise ratio is huge. Is huge not only at merger, which can be more than 10 to the 3 or 10, almost 10 to the 3. So it is really huge to perform a wonderful parameter estimation of the sources. And but even in the pre-merger phase, the best sources are the lightest one because we can detect a month before with a signal to noise ratio of 10. And so we can see the rising of this SNR. This I'm showing the median, and then we have the 67 and 19 percentile. But as we move to more massive black hole, we can detect that threshold only 3 days before merger. So these are really short transient compared to the light binary that could be in the sky for around a month. What about sky localization? Well, we discovered that it is not as good as we thought. Even we were exploiting the fact that over a month, the constellation of LISA is moving around the sun, and so it can target better the source. So we found out that initially the sky position can be as large as hundreds of square degrees, and for these light binaries, they can enter for instance, the LISA, the LSST field of view a week before. But for the more massive one, we can localize the source within the field of view of Athena of 0.4 square degrees only at merger. And so this is somewhat a limitation, even if we can exploit the power, well, I don't have time to explain the power of high order harmonic that can help us in localizing the source better. So after a thorough study, the message that I want to deliver is that localizing a gravitational wave source is possible at merger out to a redshift about 3 within the Athena field of view of 0.4 square degrees, using all the information which is associated to the very, very loud signal. And so it is the post-merger signal that we can detect. In some way, it is a pity because most of the previous studies in the literature were really trying to see periodic oscillations in the X-ray light curves, which is associated to the orbital motion of the binary. And only if we shift the binary to a very low redshift, 0.3, then we can think to discover, to point the optical LSST field of view and let Athena to scan the sky, to tile the sky over, and this requires about 3 days with a scanning pattern using at least 23 observations, each of 9 kiloseconds. So cover the area if it is possible. And then as the time progresses, you just select the area and then stare there to witness the light that is coming from these two mini disks that are emitting X-ray light because there might be a corona. So it is really, really challenging, but the message is that we can see the precursor emission on the fly, provided we see very nearby binaries with a mass, let me tell you, around 10 to the 6 solar masses. So Milky Way light black hole, but not certainly the 10 to the 9 solar mass black holes that, for instance, PTA can detect both, can detect in the stochastic background. So we are building a strategy for low latency alerts. So the idea is that we need, and now with the LISA design, we can decide to have a protected period of 10 days. So we can see the source, determine the time of merger, because this is extremely easy because the source is extremely loud. Then based on this nearby source, we can decide to have protected period, which means that the signal coming from the LISA constellation of the triangle that I showed too rapidly at the very beginning, in the protected period, only one satellite, which is housing our freely falling test masses, is in contact with the ground station. And so we don't change the constellation, which would imply a period of accumulating the data not in real time. And once we have the protected period, we can stare at the region which is pointed by LISA to witness the late in spiral merger and ring down. As far as the X-ray emission is concerned, I have only 5 minutes, sorry. We studied 3 potential X-ray observatories. O1 is Athena, O3 is Lynx, and O2 is a degraded Athena, degraded in the sense that the spatial resolution, instead of being 5 arc-second, we just put a 10 arc-second spatial resolution. And this is going to change, you know better than I, the limiting flux below which you have the confusion of the X-ray sources, both in the soft and the X-ray band. And the bottom line of this is in this figure, which is almost my last slide. So here we plotted, if we did it correctly, the calculation. Here we have the limiting fluxes in the soft and hard X-ray bands versus the exposure times. And the old Athena is this gray solid line. And we computed the flux coming from binaries that are emitting at the Eddington luminosity, correcting the X-ray luminosity, taking into account. So we counted the bolometric luminosity, we introduced the bolometric correction, and the message is that the old Athena with 5 arc-second of spatial resolution, we could really go beyond redshift or around below redshift 3 for the massive binaries that are brighter in X-rays, but we could go around redshift 1 for the less bright 10 to the 5 solar mass binaries. But if we links could really see most of the sources, but of course at the price that the sky view is too small, and so it is very difficult to spot the right area. And so with this, if with 10 arcsecond spatial resolution, we are confined mainly to very low redshift sources, but for which we can really have an exquisite parameter estimation of the sources. Considering the rates, rates are uncertain, but if sources are obscured, the situation is dramatically less favorable, but we expect it to have 7 to 20 electromagnetic counterpart in 4 years of joint observations with both X-ray, optical, and radio telescopes. How many galaxies? This is the last slide. We simulated a mock universe using a very highly sophisticated technique. So we use the Millennium simulation complemented by subgrid physics, and the bottom line is this one. The bottom line the message I want to deliver is that X-ray selection of a counterpart is vital, because if we have a merging binary of Milky Way-like black holes of a few times 10 to the 6 solar masses at redshift 2, at the time of merger, this is mainly the LISA sky localization uncertainty, and we have plenty of galaxies. But as we move to the AGN, we still have many of them, but in any case, these are the ones that have a flux limit in X-rays, which is larger than the true source. So the true source is dimmer than the average flux coming from an ordinary X-ray population. And if we go dimmer and dimmer, we can, with 5 hours of exposure time, we can really spot the X-ray source and also probably the host galaxy. So also because after the merger, we can go and have multiple observation at different times. The situation is even better, even if it is a light source, for a lighter binary, because being relatively dim, we have only few sources. So please, the message is that we should really search for dim X-ray sources as counterpart. To summarize, a typical number of AGN is very large during in spiral, but in the merger we can really reduce the number of candidates, and but it will really, we need to learn and to identify a very clear X-ray light curve that would be unambiguously tell that we are not observing a flaring AGN, but it is a true binary. As far as once we have spotted the galaxy, the message I want to give is that we should never look at, we should look at a low mass dwarf compact galaxy, not in a crowded region, but more in a low density region, because our black holes are probably are relatively light compared to the bulk of what we know about the AGN population. And I want to thank all my collaborators, because this analysis has been done also jointly with Luigi Piro, Matteo Guainazzi and the people that are working in the gravitational wave astronomy. Thanks a lot.
Thank you. Thank you. That was a wonderful tour through all of the issues going on in this very complicated field. We now have a few minutes available for questions, and I think I will take the initiative. You were saying that one of the prime reasons for the X-ray identification is just so that we can identify the galaxy that we're looking at. I've never understood, are there expected to be effects on the galaxy either pre-merger that we can detect, say, later on with other observations, or post-merger? I mean, will there be, when a galaxy has a merging black hole inside it, does that affect is that expected to affect the galaxy itself in some unusual way that is different than, say, an AGN would?
So the merger gravitational wave driven is at sub-milliparsec region. So the merger is occurring at the microparsec level. So what we are probing in X-ray is the very, very innermost region of a circumbinary disk where there is still gas, which is poured through this cavity, which is excavated. And for the pre-merger phase, unless you have a clear periodicity, which is going in tandem with the orbital frequency, with the frequency of the gravitational wave, like in this view graph I tried to have here. Maybe I can try it. No, I don't have it. Or in any way, this could be a nice view. So while we have, it's too long, while we have the oscillation of the gravitational wave frequency, which is increasing in frequency and in amplitude, if we have the same rhythm in the X-ray light curve, then we are sure. But this, we need also a very high time resolution, and this is not been studied yet. Whereas when the binary is far from coalescence, say hundreds of years, then you might have a similar configuration. So you have a circumbinary disk and you have the mini disk, but then you have time to see the oscillations only in the X-ray light curve. And you may say, this is the precursor because the gravitational wave is really too weak. So we really have few hours to spot the light. Instead, after merger, the black hole is penetrating the disk or dragging matter that can be accreted, and then we can then have more and more accurate pointings to really pinpoint the galaxy which is housing the as I was saying here, the galaxy which is housing the true merger. And we still have many AGN in the sky. The message is pick up not the brighter, but the dimmer. So we need a very, very sensitive X-ray source with a relatively wide field. So if new Athena remain with 0.4 square degrees, but there is the possibility that the spatial resolution that I heard it's claimed of 9 arcsecond can be lowered a bit, that would be fantastic, because we can avoid reaching very early the confusion limit. Let me say, do we really know what is the spectrum in X-rays? So here we are in a region of space-time with a space-time which is violently changing. You would expect shocks. You would expect an emission, maybe also gamma rays or radio from a jet, because every time we make a GRMHD simulation, we always see that thanks to the spinning black holes, we see the condition for launching a radio jet. So maybe joint radio and X-ray observation. And so we have really to think at a strategy. So with New Athena, we need to think at a strategy of multi-wavelength observation of the same event. Otherwise, it will be difficult. Coming from X-rays, I'm very fond of having a very nice accretion disk. But as the two black holes are merging, the Hill spheres around the black hole are shrinking. And so you are left with no gas around. And maybe the signature will be a dimming of the light curve and a spike and an increase, but hopefully after a few days after the merger. Because if the spike of increase is coming a month or a year, it could be just a flare in AGN that you have in your sky.
Okay, no, thank you. I know we're past the hour here. Maybe we have time for one last question, but I know people have other meetings to go to. So we'll give people just a moment here. But fascinating material. And I must admit, I'm also hoping for something slightly better than 9 arc seconds as well. And I think there's every hope that we'll get at least a little bit better than 9. So there's no reason not to.
You will do the best to lower.
Yes.
Lower when New Athena is in progress. That would be really wonderful, because I think that the science return would be really immense, also for cosmography, and
yes.
to learn about accretion in an environment that has never been tested before, and only with Lisa joining Athena it will be possible.
Okay, we have one question, which we'll have to answer quickly. Should we look for widely separated double-peaked iron K alpha emission lines, or is that something that is best suited for more separated black holes?
It's more for separate black hole, far from the merger.
Ah, okay. These will be close together?
No, because these are iron lines coming from the two accreting black holes that are separating apart.
Yeah.
But this is a good point. So I think that the research has to go parallel onto line. Discover as early as we can binary and dual AGN, and then make prediction to see at the time of merger what we are going to see. Because at merger, it's almost a point like AGN immersed in a time-varying gravitational field. And so it is in a completely different position. The good news of PTA is that we see probably, this has to be confirmed, we see a background from more massive black holes that are close enough that we know that they merge. So we have evidence, if confirmed, that in nature, two black holes coming from the merger of two galaxies can reach the milliparsec separation to be driven by gravitational wave emission, which is strong when you take the two black holes very, very close. But the mass is not the mass that Lisa will probe. So we have complementary universes that can be explored.
Okay. Well, thank you very much for a fascinating talk. I think we have to end here and end for the last one for the year. Sylvia, do you have any last?